Hello everyone, so today in this video we're going to look at the codes for the flash calculations. So in our previous video we looked at the problem with the involving flash calculations, and we derived our Riceford-Rice equation assuming that Raoult's law is valid for our case. So we derived our Riceford-Rice equation, and now let's try to write a code that will calculate the amount of compounds in a vapor phase and an amount of compounds in a liquid phase so that we can see what's happening. Okay, so let's say we're given a temperature of 393 Kelvin and the pressure of 150,000 pascals. And what else? And we're also, let's say we're given a feed of 10 moles. And let's just start to run everything so that it works. Yeah. Feed of 10 moles. And what else can we have? So in our Riceford-Rice equation, we had our Z value, right? So it was the mole fraction between two compounds for our specific case. So let's have it as an array for our question. So it's going to be NumPy array. So we said the ratio of benzene in the mole fraction of benzene in our mixture was 0.4, and for toluene it was 0.6, right? So we have it as an array here, and we can also have a variable of our Ki, right? We said that it's the saturation pressure. It's the ratio of saturation pressure to our normal pressure, so we can have our K constant as saturation pressure, PVAP, which we can find using our CHE tools over total pressure. Let's just run it. And now we want to find the amount of compounds in the vapor phase, right? So let's just have this fraction V over F represented as E. And let's just try to find E. Then using E we can find the V, as we already know our feed, right? So everything is equal to 0, right? So what we can do now is we can use our root solver so that it calculates the specific value of E that makes our sum to be equal to 0. So in order to use our root solver, we should have our function as Riceford-Rice equation so that we can plug into our root solver. So it's going to take vector, and our vector is going to be our value of E. That's going to be the first element in our vector, and it's going to return our Riceford-Rice equation. It's NumPy array, NumPy sum, right? So it's going to be sum of, so we're going to have our Riceford-Rice equation. And it should be as an array, in array form. So that our function takes a vector and it should return a vector. Okay, so so that not to miss, I'll have Z times Ki, K minus 1, and I have V over F represented as E, right? So we're going to divide by E multiplied by K minus 1 plus 1. And I should close. Yeah, let's check the equation. There are so many brackets. I should make sure that there are no errors. Yeah, this should. So I have one. Yeah, with oh, I see. Yeah, it's fine. I think now it says invalid syntax. Yeah, I think we have one more right here. Yeah. So now we can use our root solver, and that's gonna be our value of e. For root solver, we should provide our function, right, which is RR, Rashford Rice equation, and we should provide our initial guess. So let's just have 0.8 as the amount of compounds in vapor phase. No, it's for the fraction, sorry. Yes, and we should isolate it and get the first value out of the array, and we run it. So now we should be able to get our value for E. I think there is an error here. Let's check our equations. Yeah, now there was a one bracket missing, so I fixed it. And now we know that from this fraction, we know that our amount of compounds in vapor phase is equal to our E multiplied to our feed, right? We already have our feed specified above, like it's 10 moles. And our amount of compounds in liquid phase must be the difference between our feed and the amount of compounds in vapor phase. And for our x values, using this equation, we know that using the Raoult's law, we derive this equation right here, right? So we can use it. I'm just gonna copy it from this equation. And we don't have k minus I thing inside, so I'm gonna just delete it. Yes, so this is gonna be our value for for x, which is the amount of mole fraction of compounds in liquid state. And for our y, we know that our y should be k times x, right? So let's just run it. We have an error. Yeah, now it looks good. Okay, so our vapor amount of compounds in vapor phase, and we have our amount of compounds in liquid phase. We have our x values. Oops, x values. Oh, it's capital. Yep, we have our x values and our y values. But if you look at this here, we have a negative answer for our amount of compounds in liquid phase, which does not make sense. But when we talked about the Rashford Rice equation, so let's just zoom in. So when we talked about our Rashford Rice equation, we said it's only valid when it is in this phase, right? Like when it's inside of these two curves. So let's check if our case really suits that. So we have temperature of 393 kelvins, and we have and this x-axis here represented the mole fraction of a more volatile compound, right, which is 0.4. And when we go 0.4 here and go to the temperature of 393 kelvins, we can see that it is above the curve, which means it is not in vapor liquid equilibrium. And if we go to the pressure, 0.4 to 150, it is below this our curve, which means our Rashford Rice equation is not valid in this specific temperature and pressure. So that we should find specific temperature and pressure so that it's inside this curve, so that we can get valid answers for our amount of compounds in a vapor phase and amount of compounds in a liquid phase. So this was our video for code that we used to solve our flash calculation. Thanks for your attention.